Can we start?
Sir, now I'll introduce, sir. After that, we'll start the session, sir.
So
we
you
are
can
going now, sir.
see me on the slides clearly.
Sir? Hello?
I'm visible to you.
Yes, sir.
Plus the slides. Okay.
Yes, sir.
Okay, whenever you're ready, I'm waiting.
Well, 1 second, sir. We are going live, sir, in the YouTube. Once it starts, I'll just inform, sir.
Okay, no problem.
Okay. Sir, we'll start now, sir.
Okay, go ahead.
Good afternoon, everyone. Welcome to the second day of Faculty Development Program on Recent Advances in Photonics Technology. Today, we have with us an eminent personality, Dr. Rajappa Papanna Reddy, Professor Emeritus of Electrical Engineering, Purdue University, USA, as the resource person. I extend a warm welcome to you, sir.
Thank you.
Now, it's my privilege to introduce our today's speaker to the gathering. Dr. Rajappa Papanna Reddy received his PhD degree in Electrical Engineering from Southern Methodist University in 1987, Master of Science in Electrical Engineering from the University of Maryland in 1983, and BE in Electronics from Bangalore University in 1975. He has published several journals and presented many papers at several IEEE and AACE conferences during his tenure at Purdue University, North Central USA. In addition, he has published 2 textbooks in the area of optical fiber communication systems. He is now a retired professor of electrical engineering of Purdue University. His past work experience includes a senior engineer position at ISRO Satellite Center in Bangalore, staff engineer at Ares, and a principal engineer at Siena in USA. After his retirement from Purdue University, he worked on the development of design tools for OFC systems and network engineering through PR Lightcom Broadband Solutions Private Limited, Bangalore. Sir, we are very fortunate to have you with us. I once again extend a warm welcome to you on behalf of VVC fraternity and all participants. Now we shall start the session. I request the participants to post their queries in the YouTube chat box. It will be addressed at the end of the session. Now I hand over the session to you, sir. Over to you.
Thank you very much. Thank you for the introduction. So today I'll be talking on design tools for OFC systems and network planning. I'm in Bangalore, and I also thank this opportunity to give a talk on this subject matter. I certainly thank the EC department from Vidyavardhaka College of Engineering. I wish I would have been there in person, but what to do? Under this situation, we can do this to the best of our abilities. So let's look at the outline of my talk. Before I get into design tools, let's look at the overview of OFC transmission systems. That includes system evolution, and also let's talk about ultra-fast or high-speed OFC systems. So after that, I get into OFC networks. You look at the networks evolution plus the WDM networks. Then I get into overview of design tools used in industry. And mainly I'll talk about the newly developed design tools from my side, which are OFC systems are for system engineering applications and WDM nets are for network planning applications. After that, we discuss some of the initiatives from Government of India on OFC technologies. Also look at some Indian OFC tech companies. And finally, the conclusion. Okay, let's begin with transmission systems. I mean, you're all familiar with the OFC transmission systems since many years, and they offer many advantages over traditional radio frequency or microwave or cellular or even satellite communication systems. The main point here is the bandwidth, right? The glass, tiny fiber can accommodate huge amount of bandwidth. For example, the standard single mode fiber can accommodate 25 terahertz of bandwidth. Similarly, let's take an all-wave fiber where there's no water peak. That can accommodate almost 50 terahertz of bandwidth. So this is not possible with either RF or even microwave, cellular. That's the main advantage. Second advantage, it offers very low loss, 0.25 dB per kilometer at 1550 nanometer. Third advantage, no electromagnetic interference or RFI issues, unlike you have these problems with RF or microwave and satellite systems, okay? Fourth one, signal security, because the signal goes through the fiber under the ground. It's difficult to tap the signal. In radio communications, it's easy to tap the signal, right? One can easily, interfere with the RF signal or micro signal, and the security can be compromised over there. So these are the four main advantages of OFC data links. The practical systems today are 2.5 gigabits link. That's the starting point. Then systems went to 10 gigabits per second. After that, 40 gigabits per second. And now companies have 100 gigabits per second data links, and some people are using it already. When all these things happened, how these things happened? These fiber links came into picture back in the late 80s. It's very short distance. They're using short wavelength lasers or even LEDs for that matter, just a span of a few kilometers. The important breakthrough happened in mid-1990s. How? With the invention of an RBM doped optical fiber amplifier. In short, we call EDFA. So it happened in mid-1990s. That's one technology. Another technology also is very important here is the wavelength divisional multiplexing system. You can multiplex several wavelengths over a single fiber and transmit them very easily. That also happened in mid-1990s. So these two technologies, optical amplification and WDM combined gave us the long reach, right? Before that, what happened, without EDFA or without WDM technologies, they were using, reed generators, right? You want to extend the distance, you electrical to optical, OEO conversion. It's a very cumbersome process. If you change the data rate, you have to change the electronics, or you change the modulation format, you have to change the electronics. So it was really cumbersome in those years. But after 1990s, things changed, but better. Okay. Let's look at the importance of these OFC transmission systems. Well, you all know these transmission systems are the backbone of today's telecom network across the globe. Either you look at terrestrial or even under the oceans, right? Provide infrastructure for highway data transmission. And as you know, it's a critical technology for e-commerce and IT companies. Imagine, since the virus came, everybody working from home. Especially in Bangalore, I see all the tech parks are closed. With the only essential staff are working. Rest of the staff are working from home. How are they doing this? Well, they're doing this because of the great infrastructure due to this OFC technology, right? Without broadband transmission, I don't think this would have been possible. Let's go to the next slide. So anyway, what drives these optical fiber systems? As I said earlier, is the bandwidth demand, right? Main driver for this high bandwidth is the data transmission in addition to voice and video signals. Data traffic is increasing exponentially over the years due to increase of variety of cellular services. Everybody got cell phones, okay, sending text messages, looking at video, and so voice. So it's really, imagine, especially in India, we got 1.3 billion population. A lot of people are using cell phones. So obviously you see the amount of text and data and voice signal requirement. And obviously internet services, you got wireless services and broadband services and applications, so on. So you all know what are the different cellular companies in India, BSNL, very active, Airtel and others. And internet services, you got Google, YouTube, Facebook. Again, this is nothing new. Just want to mention these companies: Twitter, Flipkart, Amazon, Big Basket, and Ola, and all these things. In fact, in this virus environment, we are using everything online, buying things from Amazon. Maybe you can take a Ola, buy groceries from Big Basket, and so really it's very helpful, isn't it? Of course, several broadband applications, cloud computing, very standard nowadays for data storage, teleconferencing. Again, in this virus environment, definitely you don't want to go to a hospital. You can talk to a doctor via telemedicine, right? That's very useful. Of course, everybody got high definition TV nowadays, and also you got Netflix, video on demand. So I think this technology is really very, very vital and helping the humanity in the entire globe. Okay, let's look at some of the long-haul OFC transmission systems. This is the WDM terrestrial long-haul link, right? So you can see that we got the lambda 1, lambda 2, lambda n. N wavelengths are multiplexed together and transferred over this long-haul link. I've got TX1 for lambda 1, TX2, that's the transmitter 2 for lambda 2, TXN, N transmitter for lambda N wavelength. So this is the MUX device. It multiplexes all these lambda 1 to lambda N wavelengths. And this is a booster amplifier to boost the signal level. And here is the fiber spans. Okay, every fiber span is the inline amp just to compensate the fiber loss. And also sometimes you'll have dispersion compensating fibers as well. So they're all put together. And at the Dmax, the receive destination point, you get a Dmax which demultiplies all the wavelengths and send each wavelength to each receiver. Receiver 1 for lambda 1, receiver 2 for lambda 2, receiver n for lambda n. So as I said earlier, the typical commercial systems are 2.5 gig system. Okay, that was the old WDM system. We also call OC48 back in North America. In Europe and India and other places, we call STM16. Then afterwards, systems were upgraded to 10 gigabits per second, which is OC192 or STM64 system. Then after that, we went to 40 gigabits per second system, which is OC768 or STM256 system. Now we got 100 gigabits per second systems as well. Okay, let's look at different types of OFC transmission systems. This is the typical metro regional network, okay? So remember, any nation, any country will have a long-haul backbone network. From that, let's say you have a switch here. So switch interface, digital cross connect, which is a switch interfaces long-haul backbone network. And let's assume two cities, like one is Bangalore You got a metro core ring around Bangalore, or maybe another one is the Mysuru, okay, another metro core ring around Mysuru. So in between, you got a digital cross connect switch. So any metropolitan area network, it encompasses the city, which is called the core network. So ADM here stands for add drop multiplexer. So you can add a wavelength or drop a wavelength to the users, okay? And similarly, same thing here, okay? So you can, the wavelengths can be added and dropped to users. So these two rings are interconnected with digital cross connect switch right here, okay? So this is the typical metro regional area network. Next one. Well, this is called hybrid fiber coaxial cable TV network, right? So basically, let's take a metropolitan area network like Bangalore. So you have a master head end that has all optical amplifiers transmitter. This is the master ring, which is also called primary hub. Then you end up with a secondary hub. Then, two secondary hubs. Then finally you end up with a fiber node or optical node. From here onwards, you get the coaxial cable, okay? Coaxial cable to each home. So several homes at the user end, okay? So this is called hybrid fiber coaxial cable TV transmission systems. So combines fiber plus coaxial cable in the last mile link, okay? But now the coaxial cable links are replaced with fiber that becomes the fiber to the home system. We'll talk about that in a few minutes. Okay, here it is. This is called the fiber to the premises. You can have fiber to the building, fiber to the office, fiber to the home, anything you want, okay? So basically this architecture has a few elements here. Central office, where you got a OLT box, optical line terminal, okay, central office. So this is the starting point. Then you got a fiber link. So when you get closer to the homes or offices, you got a splitter, power splitter, 1 to N. Okay, N is the number of users. Okay, so power splitter. So basically, let's say you got a N subscribers or N users. So you have a ONU. ONU stands for optical network unit, sitting on the top of the office wall or home wall. So fiber always goes all the way to the home or to the office. So you got a OLT box in the central office, and you got a ONU unit at each destination or at each user's place. Okay, so this is the fiber to the home architecture. And another link is called radio over fiber ultra wideband. Okay, so here the starting point is the central base station. You collect all the data from users. Then you have a fiber which is running from a central base station to the random access point, the user point, okay? So you can have up and down links over this fiber. So you can have voice signals, or internet, or data signals to the users. So this is also very popular nowadays. So cell stations do have fiber links to the users as well. So these links have been utilized to transport data between wireless base station to the master station or to the users, back and forth. These links utilize orthogonal frequency division multiplexing schemes. Okay, that's the type of model format they use to transmit the ultra wideband signals in the frequency range of 3.1 to 10.6 gigahertz. So this ultra wideband is further divided into 14 subbands, each subband having a width of 528 megahertz. Let's look at the system's capacity, the trend since 1980s up to now, okay? To start with, of course, you can look at the Ethernet links, maybe start with a few megabits to gigabits. Then you got now 10 gigabit Ethernet. And also we have 100 gigabit Ethernet data links, okay? So the blue line is the Ethernet data links. Then the red line represents optical TDMA. Okay, it's not electrical TDMA. Remember that. It's optical time division multiplexing, starting from maybe close to a few hundred megabits per second to 160 megabits per second. Okay, so these are a lot of experiments were done using OTDM in a lot of universities, but never became popular. Unlike that's the WDM. Look at the green line, okay, which is this. You remember EDFA came into picture back in mid-1990s along with WDM technology. So the green line started in mid-1990s. Look at the curve. Really, this is a tremendous growth with the WDM technology, okay, to terabits per second. Yes, we do. We have lots of terabits per second capacity achieved using WDM technology as of today. Okay, let's move on to the next one. So system capacity evolution, look at 1990s, just a summary. We started 2.5 to 10 gig systems in 1990s at that bit rate, and channels were 8, then 16, then 40. Okay, channel capacities, we increased 8 to 40. The capacity achieved was 20 to 400 gigahertz per second capacity. Spectral efficiency, of course, in those times was probably less than 0.05. What is spectral efficiency? You all know that it's the ratio of bit rate to channel spacing. Okay, lower channel spacing or higher the bit rate means higher spectral efficiency. 2000s, systems operated at 10 gigabits per second bit rate. Channels went to 100. Capacity went to 1 terabits per second. Also look at spectral efficiency. Increased to 0.2. 2010, okay, so channels rate went to 100 gigabits per second. 100 channels, you end up with 10 terabits per second capacity. Spectral efficiency went to 2.0, much higher than 2000 or 1990s. Okay, future. Yes, look at the channel rate, the data rate. Each channel can operate at 1 terabits per second. Amazing, right? There are already a lot of experiments done at this rate, at 1 terabits per second. And let's say if you put 100 channels on a link, you end up with 100 terabits per second capacity. Look at the spectral efficiency, much higher than before, 20. So this is what is needed, okay, in a couple of years from now. And already there are experiments, field trials are done on this type of data rates. Well, let's look at this transmission capacity in a fiber. As I mentioned earlier, available bandwidth on an all-way fiber is about 50 terahertz. Okay, so here is the all-way fiber, the dashed one. There's no water peak on that. Remember that. It's almost like a flat loss fiber. Okay. Of course, this is a conventional standard single mode fiber. You see that the blue line. This is the water peak. So this is a problem for this wavelength band, E band. And of course, broadly, you can classify this spectrum, optical spectrum, into O band, E band, S band, C band, L band. Okay. Our WDM technologies mainly operate in this region, C and L band. Okay. Of course, in practice, how much bandwidth is available? Roughly 4 to 5 terahertz of bandwidth is available for transmission due to the available bandwidth of an optical amplifier. Even though you have enormous bandwidth in a fiber, but it is limited by the optical amplifiers on the link, isn't it? Now let's get into different types of modulus formats, up to 40 gigabits per second, okay? NRZ on-off gain, legacy format, even though people are using NRZ on-off gain format for 2.5 gig transmission or even 10 gig transmission, okay? Equipment is being utilized, even though in the field. NRZ on-off gain is called a legacy format. Then afterwards, people tried a duo-binary format. If you want to go to 40 gigabits per second, the NRZ on-off gain is probably not efficient, okay? So people tried different types of new formats like duo-binary, return to zero DPSK, or return to zero differential QPSK, or carry suppress RZ, which is CSRZ, differential PSK. So all these formats were tried for the 40 gigabits per second transmission, okay? So we'll find out soon which one is better for 40 gig transmission. Let's look at system impairments. Any communication system, whether you take RF or microwave or cellular, satellite systems, you are seeing a lot of impairments, right? In fiber links, yes, we do have several impairments. Let's look at these things one by one. First one is a linear impairment. Linear impairments arises due to amplifier spontaneous emission noise, which gets accumulated over the link. What that results? Well, that really has a negative impact on voice knot degradation. Okay? So voice knot degrades at the end of the link. When a voice knot degrades at the end of the link, it limits the distance as well. Right? You see that depends on voice knot, depends on Q factor, depends on the voice knot. The Q factor goes down, then BR also goes up, bit rate goes up. That's the problem. So another impairment is the chromatic dispersion. You're all familiar, fiber has a chromatic dispersion. It causes pulse spreading, results in intrasymbol interference. Of course, eye closure. The eye is wide open, then you get a low BR, low bit rate. Then when you move to 40 gig or maybe much higher data rates, you end up with the polarization mode dispersion. That also causes pulse spreading, intrasymbol interference, as well as eye closure. So those are called linear impairments. Okay. Of course, one can compensate the chromatic dispersion using fiber dispersion compensators along the span. Also, you can put PMD compensators to compensate the polarization mode dispersion as well. Okay. But the AC noise gets accumulated. Okay? Unless you put the nice filters, you can minimize the AC noise to some extent. So otherwise, you always end up with AC noise. So voice are always degrades to some extent. Okay. So next one is the fiber nonlinear impairments. This happens due to Kerr effect. Okay, look at any textbooks on optics, nonlinear optics. You see the Kerr effect. That gives rise to nonlinearities. So these nonlinearities are three types. Okay. First one is self-phase modulation. This is what happens on a single channel. That results in eye closure. Then if you have a WDM system, you have multiple channels present. That causes cross-phase modulation, which is called cross-phase modulation effect or multi-channel effect. That causes crosstalk and the neighbor channels. Then comes Fourier mixing phenomena. This is like, in electrical systems, we got mixing of several frequencies, right? Gives rise to intermodulation products. Same concept here, okay? Different lambdas mixed together gives rise to undesired wavelengths. That's a problem, okay? So Fourier mixing is a problem, and so it gives Fourier mixing crosstalk. So these impairments are really important. We need to control them, especially for long haul links. For shorter links, I think XPM Fourier mixing is not an issue. For long haul links, we got to do some control measures, okay? That's very important. Optimize the dispersion map and things like that can be done, okay? Okay, here is the dispersion management that I was mentioning a few seconds ago. So chromatic dispersion management is very critical for long-haul WDM transmission system to maintain the required voice knot and the Q factor levels. So we can do this compensation at 3 points. First one is inline compensation. You do the compensation and put a dispersion compensation model at each fiber span. Okay, you can, standard mode single fiber has a positive dispersion. Put a negative dispersion fiber which compensates the positive dispersion. They cancel out, right? So that can be done in each span along the link. Also, you can do pre-compensation right after the transmitter. Okay, you can do that. Or any residual compensation left at the destination point or at the user point, you can put a post-compensating fiber just before the receiver to trim the compensation, fine-tune the compensation. Okay, so that can be done. So those 3 stages of compensation can be done in a long-haul link. Of course, we need this dispersion compensator. There is both chromatic dispersion, that's the magnitude of the dispersion, plus dispersion slope of the fiber. Okay, otherwise you end up with a non-uniformity. If the dispersion slope of the fiber is not compensated, you get the non-uniform profile. That means each wavelength will have different signal power. So that's a problem, okay? That should not happen. Again, as I mentioned earlier, for very high data rate systems, you require PMD compensators. They are vital importance to suppress the PMD effects, especially at 40 gig or even 100 gig systems. We need this type of PMD compensators. Okay. Okay, let's compare this modulus formats. So you see which one is really good here. Okay. So we're looking at NRZ, unoff-king modulus format, legacy one, duo binary, then CSRZ, the carrier suppress RZ format, then RZ, return to zero DPSK format, then RZ, differential QPSK format. Okay, so you also look at the I diagram, NRZ I diagram, duo binary I diagram, CSRZ. Okay, then RZ DPSK I diagram here, RZ DQPSK I diagram right there. Okay, so those are the typical I diagrams for each format. Also look at the spectrum, optical spectrum for each format. NRZ spectrum, here it is. It's a kind of nice spectrum, compact spectrum. Here's the carrier component. Duo binary spectrum. Look at this one is in fact much compact, narrower spectrum than NRZ, right? And look at the CSRZ, there's no carrier present. Okay, suppressed carrier. So this is a little bit broader than the duo binary or the NRZ. RZ DPSK has a wider spectrum. RZ DPSK has a narrow spectrum, okay, compared to DPSK. RZ, okay. So if we are comparing this, all these formats with respect to what? With respect to noise tolerance, optical noise tolerance, AC noise basically there. And then with respect to chromatic dispersion tolerance, then with respect to PMD tolerance, then with respect to optical non-linearity tolerance, which is basically cross-phase modulation of Fourier mixing. Also, if you got an optical ladder multiplexer in a link, then you also look at what's the filtering tolerance in the way unit. And you can see the comparison. In fact, right away you can go to either RZ DPSK or RZ DQPSK. In fact, RZ DQPSK, you got all the good things for each tolerance parameter. On the other hand, look at RZ DPSK. AC noise tolerance is very good compared to DQPSK. And non-linearity tolerance also equally good. So people in industry, okay, or people choose RZ DPSK because of these reasons. AC noise tolerance is very good for longer links, okay. So the RZ DPSK is a preferred format for 40 gig bits per second transmission system. In fact, there are RZ DQPSK receivers as well, but also RZ DQPSK is a little bit complicated, more complex than RZ DPSK. So complexity, cost, the price, the performance, all put together, I think RZ DPSK is the winner for 40 gig transmissions. Okay. Okay, so that concludes those modulus formats up to 40 gigabits per second, right? Those are based on direct detection scheme, DD receivers. Remember that, okay? Just a photodiode. That's all there is, okay? Now, let's move on to this ultra-fast OFC systems. Why do we need ultra-fast OFC systems? We can probably use 40 gig systems. Well, the reason I said earlier is capacities keep on increasing yearly basis. So obviously we need more capacity. We look at capacity in terms of terabits per second. To meet terabits per second capacity, we need high data rates. So such as 100 gigabits per second or beyond, 100 or even 400 gigabits per second. So how do you handle these situations? Well, that's the reason why optical network manufacturers, even though they have a 2.5 gig, 10 gig, and 40 gig systems for metro networks, but they have to be upgraded, or they have to migrate to 100 gigabits per second or beyond to meet this demand for high transmit capacity. That is the motivation, okay, for the high speed or ultra fast OFC links. Well, of course, these are fine, but at the same time, what are the negative side of it? Okay, yes, you want to develop 100 gigabits per second or 400 gigabits per second. What are the things we have to look into? First thing is the voice requirement, right? Okay, so if you voice requirement increase by 10 dB, just by compared to 10 giga system, let's say you want to design 100 gigabits data link, so you need 10 dB more voice compared to a 10 gig data link. You need higher voice noise. Then look at the CD tolerance. CD tolerance decreases when you increase the data rate. Okay. Then what about PMD tolerance? That also decreases with higher increase in data rate. So those are the things anybody should keep in mind when you look at high data rate or ultra fast optical data links. Those are the performance considerations. Well, when you manufacture these data links, the manufacturer should also look at what is going to cost the equipment, like in terms of cost per bit, how much is going to cost per bit or cost per kilometer. These are the two things the manufacturers have to look at it as the main parameters to design the data links. Okay, so cost per bit, cost per kilometer can be reduced by using some ultra-fast coherent technologies for these high data rates. And let's see the benefits of this ultra-fast or high data links. They provide high CD robustness with electronic dispersion compensation of the receiver. So obviously, you look at coherent detection technology. Remember, direct detection technology not going to work here. So for ultra-fast data links, you require coherent detection receivers, like the one people use in satellite systems, micro systems, okay? So the technology concept is similar to radio frequency or micro systems, coherent detection schemes. So we're using a similar technique in optics at the receiver design, okay? Using coherent detection technology. In fact, the coherent detection technology came into picture even in the mid-1990s. It explored in optics, but never really got to one level unless the WTM technology and the optical fiber amplifier came into picture. And especially high data rates demanded this kind of coherent detection receivers. Okay, so with this coherent detection technology, we can achieve high capacity data links. So with this detection technology, coherent detection technology, we don't need dispersion compensation modules in the fiber span. So that simplifies the network design. So we can do the dispersion compensation of the receiver itself. That's a really plus point. Plus, another important thing, it provides high PMD robustness with adaptive compensation of the receiver as well. That means what? No need for PMD compensators in the link. So you can do CD compensation, PMD compensation right at the receiver point. Again, simplifies network design. As you all know, coherent detection technology provides higher receiver sensitivities compared to direct detection technology. That's another plus point. And these coherent detection technologies normally utilize polarization multiplication technique to transmit high data rate with lower baud or symbol rate. For example, 112 gigabits per second line rate corresponds to 28 gigabaud rate. Okay. So that's, we'll discuss this polarization multiplication techniques in a few minutes. Okay. So that's the technology we utilize in these ultra-fast systems. Also, receivers can provide non-ionic compensation of the receiver. That's another important point, okay? So what are the challenges involved with this coherent detection technologies? Well, first of all, we require a laser local oscillator having a very low phase noise, along with digital signal processing technology for carrier phase recovery. Okay, the incoming signal phase should match with the local oscillator, giving us carrier phase recovery. Okay. and require multi-level modulation formats having high spectral efficiency. We'll look at different multi-level modulation formats for these coherent detection schemes. Also require high resolution A to D and D to A converters. And require optical carrier phase estimation DSP algorithms. We require electronic chromatic dispersion DSP composition algorithms. And we require fiber nonlinearity DSP composition algorithms. Also, we require adaptive PMD DSP composition algorithms. Look at this. All these can be done using DSP technology at the receiver. What is amazing, isn't it? Okay, in the DD case, it is not possible. In the DD receivers, the coherent detection receivers, DSP is a big advantage to compensate the chromatic dispersion, to compensate the PMD effects, and to compensate the non-linearities of the fiber. Great advantages. Okay. Of course, the transmitters and receivers become complex. DD transmitters and DD receivers are simple. They're not that complex, but compared to them, coherent detection transmitters and receivers become complex. But you get the benefits, let's not forget that. Okay, here's the typical PDM QPSK coherent transmission for 100 gigabits per second. Okay, sometimes you also call PM, polarization multiplexing, or polarization division multiplexing. Okay, PDM QPSK transmission. So you get a QPSK modulation here. And as I said earlier, it utilizes polarization multiplexing technology. Here is a laser light. That signal is split into two polarization, X polarization, Y polarization. And the X polarization, you need one set of transmitter module based on also this RC pulse carver is there to get the RC pulses. And this is the auxiliary interferometer with the pi/2 shift for QPSK format. Okay, so for Y polarization, you need one set of transmitter components. For X polarization, you need another set of transmitter components. Okay, auxiliary modulator plus the RC pulse carver. Okay, then you combine the polarization and transmit over the fiber. So this is the transmitter side. The receiver side, you got the polarization splitter, X and Y. X goes to one part of the receiver, having a photo detection, having a 90-degree hybrid. For the X side, X polarization. For Y polarization, you get a similar set of receiver components. Then comes here unlocked digital conversion, then DSP. So here is the DSP chip. This does all those things which I mentioned. CD compensation, PMD compensation, and fiber nonlinearity compensation. Okay, so this is the typical receiver, coherent receiver. This is typical coherent transmitter. For the two modules are more complicated than the DD transmitters or DD receivers, but you got the benefits of achieving higher capacity. Also, let's look at another modulation format for coherent detection technology. Is called PDM, which is polarization division multiplexing, M-array CAM transmission. Okay, M can be 4, 16, 64, or 138, or even 256, right? M-array CAM. It's called multi-level CAM transmission. Okay, here is a similar concept. Okay, similar type of transmitter components, and this is the you need pre-processing circuitry before the transmitter modules to kind of put them into proper data stream. Okay, and so X polarization component, Y polarization component. Again, you got RC pulse carvers is the transmitter side. Receiver side similar to what we discussed earlier in a QPSK scheme, similar to that. Okay, so this is M-array CAM transmitter and receiver. Okay, this slide gives a summary of all these coherent ultra-fast OFC systems. Okay, you can see the format, different formats. PDM QPSK, the first one we saw earlier at 100 gigabits per second. Then you get CAM, 16 CAM, PDM 16 CAM, PMQPSK at 400 gigabits per second. This one is at 200 gigabits per second. PM 8 CAM 400, PDM 16 CAM at 400, and similarly PDM 32 CAM, 64 CAM at 400, and you can see PDM 32 CAM at 1000 gigabits per second. That's what 1 terabits. Likewise, you got PDM 64 CAM at 1 terabits per second. And this is the line rate, also called the bit rate standard. And the corresponding symbol rates are right here. Okay. Number of bits. You can see number of bits increases with higher M value. 256 has 16 bits. Okay. 256 CAM has 16 bits. And spacing. 50, I think should be gigahertz here. 50. So spacing is given. Spectral efficiency, you can look at spectral efficiency. For PDM QPSK 2, then obviously if you higher the M value, you get the spectral efficiency increases, right? You can see for 250 CAM, spectral efficiency is almost 8. Okay. Number of channels and the data link. So here are the number of channels. Capacity achieved. 8.8 terabits per second for the PDM QPSK operating 100 gigabits per second. Let's look at maybe some 400 gigabits per second. This one, same format, PDM QPSK. Okay, spectral efficiency, capacity, right? 8.8 almost. Similar capacity. Of course, if you need higher capacity, you should go to higher M value, such as 64 CAM or 256 CAM. 35 terabits per second. Okay, so higher the system capacity means higher the M value. So that's what you have to do. Obviously, higher the M value, that means you need higher OSNR levels. You see that, okay? So for example, look at this 256 CAM PDM, you need OSNR higher than 30 dB. So that was a challenge to get that kind of OSNR. Whereas PDM 16 CAM is much, requires 19 dB OSNR. And look at the PDM QPSK, much less OSNR, 12 dB. So that's the reason why in industry people utilize PDM QPSK receiver for 112 gigabits per second transmission because it requires less OSNR compared to M-array CAM formats. Okay, of course, if you increase the data rate, obviously you need to go with higher M-array CAM formats that requires high OSNR levels. Okay, let's move on to the next slide. Here I'm comparing spectral efficiency limits for the coherent ultra-fast systems. On the y-axis, you got spectral efficiency in bits per second per hertz, and the x-axis, you got required OSNR per bit. Okay, so you're all familiar with Shannon's theorem. This is the Shannon's curve. Okay, the dark black one is the Shannon's limit, a Shannon's curve. The yellow one is for the M-array CAM format, M equals 4, M equals 16, M equals 64, M equals 256, M-array CAM format. Of course, away from the Shannon's limit. And what are these square red symbols? These are the experiments or the field trials conducted on the M-array CAM format. 4 CAM format right here, spectral efficiency close to 1. 16 CAM formats, 3 field trials right there. Then 32 CAM, 128 CAM. Okay, you can see that, in fact, there are a lot of experiments conducted with 16 CAM because why? 128 CAM, 32 CAM requires high OSNR levels for transmission. 4 CAM is really gives a less spectral efficiency. Of course, you may end up with less OSNR here, but you don't have a higher spectral efficiency. But look at 16 CAM, gives a reasonable spectral efficiency, but also a reasonable OSNR requirement. Right? Of course, higher M CAM formats require, they give high spectral efficiency, but they require high OSNR levels. That's the only negative thing. Otherwise, they give high spectral efficiency. So looking at these M-array CAM formats, looks like 16 cam is the right one because it gives pretty good spectral efficiency. At the same time, it requires less voice knot levels. Okay, that's a benefit of 16 cam systems in coherent detection technologies. Okay, so those are the system aspects. Let's move on to optical fiber networks. So again, here I will give an overview on optical fiber networks. Okay, what are these optical fiber networks? Okay, let's understand some of the fundamentals. Then we'll talk about design tools. I know I'm spending more time on systems and networks, but again, I'm sure some of you already know some of the things, but I just want to give an overview on these system networks. Then we'll look at the design tools. Okay. So the optical fiber networks across the world provide broadband infrastructure for data transmission. Okay, we already discussed this before. Okay, so the growth of internet or the worldwide web applications has resulted in greater need for high bandwidth transport networks. And you got the voice and video and data that's driving the bandwidth requirements. Of course, technologies adopted the backbone of the network. Have migrated close to businesses, government offices, colleges, universities. That's how so many networks evolved, in any country, okay, or in metropolitan regions. This is a typical slide, optical fiber network. You can see the USA map here, and the undersea or the submarine data links going to other parts of the globe. And these are the metro regional networks utilizing WDM technologies. Okay, typical India backbone network. This is again old picture, so you can see the fiber going from north to south, east to west. Okay. Okay, let's just review some of the fiber networks. Basically, the first one is the first generation network. At that time, they replaced copper lines with optical fiber. Very first one. Okay. So during that time, the switching and processing functions were performed using electronics. Okay, single wavelength operation, no WDM, nothing at that time. Okay, then afterwards, the WDM came into picture in the mid 1990s. So they called them second generation networks based on WDM technology. And what are first generation networks? Well, the examples of first generation networks include the fiber distributed data interface, FDDI, then SONET, synchronous optical network, that's for North American standard. Here we call SDH, which is synchronous digital hierarchy, Europe and Asia. Variety of enterprise networks were evolved, ESCOM, enterprise serial connection, fiber channel, EP, high performance parallel interface. So these are the typical first generation optical networks, okay? And I'm sure you've seen SDH data rates. The last column gives the bit rate for each format, okay? And OC1 51.84 megahertz, as in those days, such a low data rate. Because nowadays we got the OC768 close to 40 gigabits per second, and in fact, now even more than this, 100 gigabits per second. Okay. These are the typical layers in a network for first generation. Layer one, a physical layer, that's the optical fiber link. Then the word that they get data link, network layer, transport, session, presentation, application layers. Several layers on the network. Okay. Second generation networks, as I said, these are based on WDM network. They replace all the traditional electronic switches. So WDM technologies was introduced into the network, resulting in an optical layer that provides services to different client layers, such as Internet Protocol, IP layer, SONET, or ATM technologies. And as I said earlier, WDM optical networks were deployed in area region. Second generation network, this is optical layer. This is the optical layer, lies above the physical layer. These are the SONET SDH nodes, okay? And what are the client layers? Client layers reside above the optical layer. These layers are Internet Protocol, SONET SDH, ATM, Ethernet, ESCOM, and so on. In WDM networks, of course, most important thing is wavelength routing. You got the n number of channels. How do you route the wavelengths on a network? You see see this diagram, how the wavelengths are routed. Lambda 1 is routed with node 1 to node 2, or lambda 2 is routed with node 5 to node 4, and so on, okay? So basically, when you route the wavelength, we call that as a lake path. So a lake path connection is established between a source and a resistance node pair, based on certain routing wavelength algorithm called RWE algorithm, okay? Architecture. Optical link terminals are placed at the end of the links in a network, okay? Also, we have optical add-drop multiplexers are utilized at the destination location in a network where wavelengths can be dropped or added. Also, you get optical cross connects that enable mesh topologies and switching of wavelengths in a wide area network. And we already discussed the client networks such as ATM, SONET, IP, all those things. And you need switches for all these client layers. What are the different WD network elements? Well, you need transmitters, receivers, MUX, DMUX devices, optical add-drop multiplexers, optical routers, switches, cross connects. Sometimes you may need wavelength converters, of course, optical amplifiers to overcome the losses. Then you need transponders, some passive elements, combiners, splitters. So all these are very important elements for a WDM network. Okay, let's talk about what is network planning. Okay, so let's say somebody wants to design an optical network for a greenfield environment. You have to start somewhere. So first you do the planning aspects as efficiently as possible. So first thing you need to find out how many wavelengths you require. So number of wavelengths on each WDM link need to be determined, including the number of add-drop ports and the sizes of optical cross connects and OLTs. OLTs are optical line terminals. Capacity planning can be done efficiently by monitoring the real-time traffic and considering its statistical properties. So based on the network traffic, a network should be able to efficiently route the traffic between source and node pairs. Right? These are the design guidelines or requirements. So also one should establish network protection or restoration mechanism. It sometimes can be a single failure or a double failure or multiple failures, right? Fiber cut can happen or node failure can happen. How do you provide this protection restoration mechanisms in network? That's very important. And also one should be able to evaluate performance limits, performance metrics like blocking probabilities based on targeted bit error rate or OS values. And consider short-term, long-term capacity planning. Maybe network should be operational for 5 years, or maybe what happens for 10 years time or 15 years time. That's long-term capacity planning. How do you upgrade the network in that case? Okay. So you need to look at all these considerations. So standard RWA problem in WDM networks. So given a network topology and a set of light path requests, which has find the shortest route and the number of wavelengths that minimize the blocking probability, right? That's the criteria to find the number of wavelengths in a WDM network. Another, if no wavelength conversion is available, then light path must use the same wavelength over all the links. That's another constraint of the design. You have to take into physical air impairments like AC noise, fiber nonlinearities, and so on. Network resources, how many fibers, how many wavelengths, things like that. Then fault tolerance, survivability issues, all these things should be taken into account when you look at the network planning. So general RWA problem is not easy to solve. In fact, it's really difficult to solve even for a fixed routing scheme that requires some mixed integer linear programming technique. Okay, so this mixed integer linear programming technique is really complex. It requires and also is computationally expensive. It takes a lot of time to compute the to solve the RWA problem. The problem becomes even more harder if routing is not fixed for a specific wavelength assignment scale network. So in this case only you can do the simulation. So what are these network survivability issues? Related to the network ability to ensure service provisioning in the presence of failures. Okay, so survivability issues includes how to provide link and path protection mechanisms. Each working light path is assigned a spare wavelength to survive a link or a node failure. So this is an important topic, definitely it has to be taken into account. WDM network management. Well, this slide shows all the main elements. Okay, so here is the optical network mesh topology. So we call transport plane. Then more than a control plane that interface optical nodes control, routing mechanism, protection mechanism, light path definition. Then photonic manager plane, fault detection, inventory, operating, supervision, all these things. All these are elements will become a part of WDM network management. Okay. Then obviously one has to look at the cost aspect. So obviously you've got two components. One is the capex, minimize material cost, that means all the equipment cost. Avoid regeneration, okay. Then minimize optical airtrap multiplexers, optical cross connection, and so on. Then minimize operation cost. Okay. Day-to-day operation cost or monthly cost, okay. So those are the things you need to take into account. CapEx and OpEx are the important components for the network cost. Okay, let's look at some initiatives from the Government of India. Of course, we have Department of Science and Technology back in Delhi that monitors fiber optic technologies or telecom technologies. Along with it, we have a CDOT, Center for Development of Telematics. We got the one in Bangalore and Hyderabad, other places, also back in Delhi. So they initiated quite a few photonics initiatives since many years. They called integrated photonic research initiatives. Also, remember, Digital India is a very popular thing since many years. Then, government National Optical Fiber Network. We'll talk about that in a second. That can provide broadband connectivity between government offices, cities, even villages through this National Optical Fiber Network, plus fiber to the Gram Panchayat, and so on. So here it is, National Optical Fiber Network. Okay, here is, in fact, you can look at this website and learn more on this optical fiber network. It's the world's largest rural broadband connectivity project. It accommodates about 2.5 lakh Gram Panchayats in India to be connected. I'm sure they're putting all the fiber to several villages. It takes some more years to implement this project. They want to provide at least a minimum of 100 megabits bandwidth to each village. Okay, about 6 lakh kilometer new incremental optical fiber to be laid. I'm sure they're still working on it. Indigenous equipment design, manufacture under Make in India project. Okay, in fact, the company called Tejas Networks back in Bangalore is involved very actively with this optical fiber project. They're also supplying fiber to the Gram Panchayat data links based on gigabit PON technology. GPON technology is being used across India. Okay, so Tejas also is supplying this technology. And of course, centrally located high capacity network operation center and network management service to monitor and ensure uptime and network provisioning. Wi-Fi connectivity at each optical network unit in the cities or villages also to be accommodated. Okay. Okay, let's look at some of the Indian OFC tech industry. I guess most of you are familiar. Sterlite Optical Technologies manufacture optical fibers. Ox Optifiber, another company also involved with the manufacturing of optical fibers. Optical Photonics, this is right in Hyderabad. They manufacture optoelectronic devices. And cable TV companies, starting with Asianet back in Kerala, Hathaway, FiberNet, all these guys. HFC, the provide HFC cable TV, fiber to the home services. Tejas Networks, I mentioned, they manufacture WDM equipment, and Ethernet optical equipment as well. United Telecom, WDM long haul system, FIBCOM, WDM networks. Of course, service providers, you all know, Reliance, Jio, in fact, is invested a lot of money on the fiber links. They're putting fiber to the home. data links. In fact, in Bangalore, I've seen a lot of places they're doing that already. And Tata Communications heavily involved with the fiber links. BSNL, Railtel, ACT FiberNet, they're providing fiber to the home data links in Bangalore and other places as well. So design and development of active, passive photonic devices is definitely essential to configure the system networks. Because right now we're getting all these components from other companies, integrating all these devices and manufacturing equipment in India. Also, we are buying equipment from abroad as well. Okay. So I also feel that there is a strong need for photonic research centers at the Indian universities for students to pursue graduate studies, MTech, PhD programs. Of course, in the Indian Institute of Science and the other IIT campuses certainly involved with this, fiber optic research, systems and networks areas. But then I think I see in the college level, at the university level, I think maybe we need some more support in the administration to establish these photonic research centers. That will be helpful for the faculty members, also for the students as well. Okay, now comes the design tools. So what are these photonic design tools? Well, let's start with device modeling and simulation, right? You got lasers, diodes, and photodetectors. So you should definitely can do the device modeling and laser diodes or photodetectors. You can optimize the design of these devices. Or optical fibers, optical amplifiers, filters, external modulators, integrated optics, passive delays. All these devices can be modeled, simulated, okay, using a photonic design tool. Then comes, yes, when you have the systems like transmitter system, receiver system, or data links, long haul links, or cable TV links. So what do you do? Then you need system design tools as well. Okay, so you need also you need to have a system modeling and simulation tools for modeling different models formats. And as on King, do binary, RWE, PSK, all the things we discussed earlier. Then obviously the system modeling tools should give us the results, system performance metrics such as BR curves, Weisner curves, linear and non-linear impairments. They should model linear and non-linear impairments. Find out the optimal launch powers, what's the maximum transmission distance along a link. So these estimates should come out from the system design tools. Because if we use coherent receivers, we need DSP algorithms as well. For network design tools, you need static and dynamic network planning tools should be available. You need to have physical topology design, light path topology design. Then you need to model different node architectures. You need to look at the network survivability aspects. You need to model physical layer impairments. Then you need to find the optimum RWE algorithms for route selection, also for wavelength assignment. Okay, and you need to find the quality of service and find out the cost requirements. Get the estimate on the light path blocking probability and the network reliability, and so on. So these are the network design tools. Okay, we need network design tools to get the estimate on all of these requirements. Okay. So now let's look at what is available in the market. Photonic device or system simulators. In recent years, commercial photonic simulators such as VPA component maker, that's for device modeling. Even you can use transmission maker for the system modeling. Okay, component maker for the device modeling, VPA transmission maker for the system modeling. That's a VPA company. Other one called OpSim, which is formerly it was called RSoft for system simulation or modeling. Photosys is another company for system modeling. OpSim also. OpSim in fact is RSoft. Optical system is the Canadian company. That's different from OpSim. Okay, so OpSim is the RSoft company which is used for system modeling. So these packages are very popular for photonic devices and systems in academia as well in the industry. Okay, and these photonic simulators are based on time-domain simulation techniques, and they solve Schrodinger equation numerically using Fourier split step method for long haul links. And the computation of BER requires either semi-analytical or Monte Carlo simulation techniques. Although these simulators are accurate, but the simulation time is really consuming. It takes several hours, particularly for long haul WDM system networks. And in addition, these commercial simulators are certainly expensive. Okay. Now let's look at what are different WDM network planners or simulators. In recent years, there are several network simulators came into picture, such as VPA link configurator for network simulation. Metro One belongs to probably RSoft application. Metro One for metro network simulation. WONS is a university simulator. NS2, NetPlan, MatPlan, WDM, OpNet. These are the things freely available. Okay. So they utilize, one can utilize them for network planning and design. So some of these network simulators utilize simulation approach for traffic arrivals, blocking probability calculations, and of course they are time consuming as well for the analysis of complex WDM optical networks. And of course, in addition to this commercial device simulators or network simulators or system simulators, you look at optical network equipment manufacturers. They have their own in-house design tools for systems, also for networks. Of course, these tools, design tools, are proprietary, right? I mean, they don't want to give to other people. Yes, they're not available for colleges and universities. And of course, these tools are quite expensive for academics. There's a negative point in terms of cost element. So, due to these reasons, so after retirement, when I came back to Bangalore, I thought let's develop some simple design tools for systems and for networks based on analytical models. I don't want to deal with numerical models. Schrodinger equation takes a lot of time. If you have WDM 64 channel system, it takes hours to compute bit error rate. Okay, you use the Schrodinger equation and our Monte Carlo techniques. It takes a lot of time. So I thought, so for the colleges and universities, I thought simple analytical design tools will be good enough to get a feel for the systems operation, also for network operations. Okay, so let's talk about OPC system software. This is the analytical design tool for system engineering. Okay, so basically it's based on Java GUI, which performs system analysis, design, and optimization of various types of fiber optic links. Remember, I talked about fiber to the homes data links, or point-to-point data links, or WDM links, or radio fiber links. So we can model all these links and look at the performance of all these links using system software. So it doesn't take much time. So I use all the analytical design formulas to model these transmission links. Okay. So again, I want to emphasize that web system is not a simulator, okay, but a system engineering toolbox developed by my company, which is PR Lightcom Broadband Solutions, right here in Bangalore. Okay. And this system software offers the following advantages over the existing commercial photonic simulators or models. So as I said earlier, it's based on analytical PR models, no need for simulations, and definitely fast computations, quite interactive, requires minimal training for the students. And I've included several design examples in the system software for easy understanding. Also, I've included a user guide in the system software that contains the analytical modeling details for each link configuration and system design considerations. I don't want students or the faculty members to assume this is like a black box. It's not. So you want to understand how I computed PER or OSNR, things like that, in the system performance metrics or blocking probabilities. How did they compute? So you want to look at the theory and the models behind these computations. So if you look at the user guide, you do get the picture how you computed all these parameters. So you need to understand. That's very important. Okay. And as I said, interactive, self-learning, minimal training. It can be installed or configured on Windows or Mac systems. Okay. So I want to, of course, I thought of doing some demos. I don't think I can do this now because of the lack of time. So maybe you can download my design tools later on. I'll tell you how to download them at the end of my talk. So I'll just give you a picture. What can you do with the system software? design tools? Well, you can design links. For example, let's say you can design a point-to-point data link, gigabit Ethernet link. Okay, so I just quote you some examples that you get an idea behind the system software. Okay, so one can design a long reach link for a bit rate of 10 gigabits per second, operating at 1550 nanometer with a BR of 1 E-10. Those are the design requirements. So you can find out what is the maximum distance possible, what is the required launch power, what is the receive sensitivity level. All this you can estimate from my software. You can also specify the type of transmitter required, specify the type of fiber required, transmitter and receiver. You can change all these things. You can change the fiber, change the transmitter type, receiver type, so you can get different results. So these are the things you can do using system software. So another example, like let's say you want to design a fiber to the home using GPON technology. So you want to design an upstream data link at 1.244 gigabits per second over a standard single mode fiber at 10 nanometer for 32 users, having a BAR of 1 E-12. Another example, you can look at design an all digital video short cable TV link, having a NTSC format for 64 cam with 30 cam SCM channels or a standard mode single fiber at 1310 nanometer. This is the HFC cable TV link. Then radio over fiber link. You can design a radio over fiber link or a standard single mode fiber at 1310 nanometer, assuming a QPSK model format. Assume 50 data subscribers along with the RF amplifiers, each having a gain of 20 dB. Find the required laser transmitter and user receiver signal levels. So, I'm just quoting typical examples. And then you can create your own examples. It's not an issue here. Just to get an idea what the system's soft can do. And let's say you want to design a WDM long haul link. So you want to design a 16-channel WDM long haul link or a standard single mode fiber operating at 10 gigabits per second with 50 gig channel spacing. Assume 100% Indian compensation and find the optimum power fiber launch power levels and the maximum transmission distance. Okay, these are the typical things engineers do in the real world. When you design a fiber to the premises link or a point-to-point Ethernet link or cable TV link or WDM longer link, these are the problems engineers solve in the industry. And I validated my system soft with published literature. Okay, so I validated the WDM link with some published data in IEEE Photonics technology letters. So I compare my blue line is from the system soft, the red line is from the this IEEE publication. So you comparing Q factor versus launch channel power, they're pretty close. And also comparing voice-NAR versus distance, okay? With and without Raman amplification for long haul applications. Voice-NAR on the y-axis, distance on the x-axis. You can see the blue line is system soft, OFC system soft, and the green one was some publication from the Finisar Corporation. Okay, they're pretty close. And just show you typical bit rate versus transmit distance for the dead detection formats. I looked at all the three formats here: energy on-off gain, RZ DPSK, RZ DQPSK, BR versus transmit distance for a bit rate of 42.8 gigabits per second. So you can see that the top black one is NRC on-off gain, gives a higher bit rate. Then RZ DPSK, RZ DQPSK is the red one, much better than NRC on-off gain. The best one, you can see RZ DPSK, gives a lower bit rate and longer distances. So that's the reason why people use RZ DPSK format for 40 gig transmission systems for long haul WDM transmission. Okay. Also, I got bit rate versus distance for high-speed formats. We discussed the coherent modulation schemes such as RZ TPSK and PM 16-cam multi-level formats earlier. So using work system soft, I looked at the BR versus distance for a bit rate of 112 gigabits per second transmission over a large area fiber link. So you can see this red one, PM16COM. The PM16COM format is higher BR. And look at the black one for PM. The black one is RCDPSK. RCDPSK format. You can see the RCDPSK is the black one. The blue one you see. Blue one is a PMQPSK. Initially, PMQPSK gives a little bit higher PR compared to the RCDPSK, but over longer distances, you can see this PMQPSK yields lower BR compared to RCDPSK. Okay. So those are the OFC systems of results. Now let's look at another module which I developed called WDMNetSoft. So it's a network planner. So this planner is designed for greenfield metro regional long-haul transport optical networks. We don't require any regenerators here. Developed by my company, which is PR Lightcom Broadband Solutions. Assume optical networks having mesh and ring topologies here. So you can have a network that has a mesh topology, which is typical for a backbone network. Or you can assume a ring topology, which is a standard for a Bangalore metropolitan region or Mysuru metropolitan region, like that. Okay. Assume static or fixed traffic matrix for the network service provider. Even though in real world traffic is dynamic, but when for planning, I think you can assume a fixed or static traffic matrix to start with. Okay. Then assume bidirectional fiber links between the node pairs, and each fiber link carrying a set of doublet number of wavelengths, WDM channels. Okay. So here I use a static RWE engine to estimate the required number of wavelengths per link. Assume a wavelength continuity constraint. And also we model physical layer impairments, linear impairments and non-linear impairments on the network. Okay. Then we also consider various modulus formats along with multiple line rates. We compute performance metrics such as optical to signal to noise ratio, bit error rate, and Polson PMD effects for each light path. We also estimate light path blocking performance in the network. Consider node architectures. Currently, we're using legacy optical cross-connect nodes and typical fiber spans. Also, we look at this fault tolerance analysis. Currently, we use only single failure only. Look at the primary paths and the backup paths. Perform relative cost analysis on network. Also generate routing tables, performance plots, and summaries. So let's talk about static RWE engine. Static RWE engine performs the following functions. First thing, the routing. What is the shortest route? You want to transmit data between source node and destination node. You need to pick up the shortest route on the network. How do you do that? Well, basically a shortest route between a pair of nodes is found by applying a standard Dijkstra algorithm on the network. And once you found the shortest route on the network for a given source and node pair, how do you assign the wavelength? Well, when searching for available wavelengths and the shortest route, the lower index wavelength is chosen first before a higher index wavelength. It's called first frequency assignment. Okay. So RWE engine assumes static traffics between each node pair. Single light path connection between a pair of nodes represents the client traffic in gigabits per second. I'll show you the static traffic matrix in few seconds. Similarly, the light path connections for a particular route represent three client signals, say OC12 wavelength or OC48 wavelength or OC192 wavelength. So let's look at the traffic matrix in the next slide. That way you understand what I'm talking about. Okay, here is
Sir?
Yes.
Sir, please continue, sir. Now it is resolved.
Okay, thank you. Okay,
Thank you, sir. Thank you.
the PLI RWE flowchart earlier. So using this flowchart mechanism, one can compute the light path blocking probability. Well, let's just review this in a few seconds. So first, know the traffic matrix, run the static RWE algorithm, then select the shortest route, then run the PLI evaluator. Okay, that means you add all the physical aid impairments and compute BR, OS, NAR, and so on. Then test BR. So computed BR is less than or equal to threshold. The requirement BR, the one we need. If less than that, then your light path is established, right? Okay. If it's not, if this one does not satisfy the threshold BR, the one we need, then you block the light path, then you count the number of blocked calls. Then based on that, you compute the light path block rate as a ratio of number of blocked calls over total number of light path demands. So that's why you get the light path blocking probability. Okay. And I'll show you some figures that computed light path blocking probability on different networks using WDM NetSoft. So on the y-axis, you see light path blocking rate in terms of percentage. On the x-axis, you see percentage of light path connections. So we examined the 3 networks. One is the India network, National Science Foundation network, that's a US one, NSFnet. Another one is Euro network, European network. 3 different types of optical network topologies. And we use modulation format RWE PSK at a bit rate of 40 gigabits per second. And we set bit rate threshold, we need 1e minus 4. Okay. If this criteria is not met, then you get the blocked calls. Calls will be blocked. So look at the red one for the NSFnet. Okay. So basically, initially, you start with 20% block rate, then as the number of light path connection goes up, the traffic goes up, your blocking rate also goes up. And this is for the India network, and this for Euronet. Looks like Euronet has the lowest blocking probability rate compared to IndiaNet and NSFnet. It depends on the topology, configuration, number of nodes, and things like that. Okay, so you have to look at the network topologies. So Euronet, is a smaller topology compared to IndiaNet and NSFnet. So that's why you end up with a lower blocking rate for Euronet. Okay. So also this WDM NetSoft provides cost analysis. So the static network planner computes the relative cost of the network taking into account the following aspects. Link cost. What is the link cost? That includes the cost of the fiber, installation, and passive elements. It also includes the cost of the fiber span links. That includes optical amplifiers and dispersion composition modules. It also includes the cost of each node. You can have several nodes in a network, right? That includes the MUX, DMUX elements, cross connects, switches, amplifiers, and transponders. So you got to take into account the cost of all these elements. This is the WDM NetSoft main window. So here is the typical NSF network. So here is the links connecting different nodes or different states or cities. Okay. So this is the east coast of US. This is the west coast. I think there's some crosstalk going on here, so let me understand. So here is the load traffic
Group
Hello? There is some crosstalk happening in the background. Can you
Yes, there is. 1 second, sir.
Yeah, the crosstalk in the background.
Sir, you can continue, sir.
Okay, so I was saying, see, this is the 14-node NSF network, sample network we modeled using WDM NetSoft. So here is a traffic matrix. Because there are sometimes mostly one connection between each source node and destination node. Node 1 to 14, node 1 to 14. So load the traffic matrix and do all the calculations. Okay, let's go to the next slide. So here is the fiber span parameters on the network. Okay, we use fiber type standard single mode fiber, attenuation of the fiber, 0.25 dB per kilometer, fiber span length, 94 kilometers, number of spans, dispersion. So all the fiber properties are included here. Okay. And inline EDFA, amplifier parameters, noise figure, launch ripple, PMD coefficients, and so on. Then inline EDF, second EDFA, noise figure, and amplifier chain ripple, and so on. And dispersion compensating fiber parameters, fiber type, attenuation, dispersion, all those things. So you can, include all these fiber span link parameters in the WDM NetSoft as well. And node properties, what are the input channel power, multiplexer loss, tap loss, demultiplier loss in the node, insertion loss of the node, waveguide loss, all this switch crosstalk ratio, all these parameters can be modeled in the node module. Okay. So using these design tools, we did some pilot projects in Bangalore. We conducted pilot projects, back in 2018, I think, 2018, yes. Conducted pilot projects with the EC Department of BM Scholars of Engineering, Bangalore, during fall 2016, sorry, not in 18, 2016, in a PG course in optical communication networks. So OFC systems was used for gigabit Ethernet and WDM link engineering case studies. Okay, I gave some case studies for the students in the PG program to the realistic case studies, okay, for gigabit Ethernet and WDM studies, case studies. Also, we introduced WDM NetSoft in the PG program to analyze the blocking properties of a destabilizing ring and mesh networks. Okay, we formed a ring around Bangalore metropolitan area, and they computed the blocking properties and understood the fundamentals. Also, mesh networks, the backbone networks, they model it. So suddenly, based on the students' feedback, we got the appreciation. They appreciated the practical aspects of system engineering as well as the WDM network design aspects. So basically, we come to the end here almost. This is almost the last slide here. So I presented an overview of the systems and networks along with the newly developed design tools, which are OFC System Soft and WDM NetSoft. So for more details on the design tools, certainly you can visit my website, which is www.opticalnetworktraining.com. So you can go to the resources tab and that website. I put down all the white papers and the details of these software modules. Okay. So you can certainly read and understand more about these two design tools. And today's presentation slides, along with the design tools, System Soft and WDM NetSoft, are placed in my Google Drive. Okay, somebody who wants to really download the OFC System Soft and WDM NetSoft for their studies, either a PG curriculum or undergraduate curriculum, or even faculty research, certainly you can send me an email. Okay, it's a free download, so one can utilize these two tools for your coursework. Okay, so they're on my Google Drive. So once I send the email, once I get the email request, then I can send you the link to download these two software design tools. So here is my email ID, rpapanna@gmail.com. Okay, so certainly whoever is interested, can contact me for these two design tools. And these are the references. That's what it is. Okay. So any questions? Certainly appreciate you guys. Okay, over there. Any clarity, any things you want to make comments, you are free to do that. Okay.
Oh.
Yeah.
Thank you, sir. Yes, sir. Tell me, sir.
Okay. I hope all the faculty members and the other participants today understood these systems and networks, also understood the fundamentals of System Soft and WDM NetSoft design tools as well. So again, for further details, you can contact my email, or if somebody wants to utilize these design tools, I can send you the link to download. Okay.
Definitely, sir. Definitely. Thank you very much, sir, for your valuable.
No problem. Thank you very much for the invitation. Okay.
Thank you, sir. Thank you, sir. Some questions in the chat box are there.
Okay, chat box. I have to go look at the chat box and I will answer that.
I shall read them for you, sir.
Shall I close this one now?
No, sir. No. Don't close it, sir.
Okay.
Shall I read the question, sir?
You read the question and answer. Yeah, that's better.
Okay, sir. The first question is from Lakshmi Madam. What is the impact of roll-off factor in Nyquist wavelength division multiplexing?
Roll-off factor in the filters.
Yes, sir.
Yeah, definitely roll-off factor is definitely important in filter design. WDM, mux or DMux, the roll-off factor is an important thing. Okay. So yes, basically, again, depending the filter roll-off, you can maybe crosstalk could be an impact. It can impact the crosstalk between the channels. Okay, if you have a ROADM filter or any other filter, okay. So if you have not a very good roll-off, that can cause some crosstalk issues. Crosstalk issues between the channels. Okay.
Okay, sir. Okay.
Yeah, flat roll-off is wonderful. Like a brick wall type of response. So there's no issue. But if you have a very Gaussian roll-off, things like that, that can have some impact on the crosstalk, switch crosstalk or filter crosstalk. Okay. Yeah.
Yes, sir, yes. And next question is asked by Amsa Madam. That is, why are EDFA used in a transmitter?
Say it again.
Why are LBM doped fiber amplifiers used in a transmitter?
It's not in it's after the transmitter. Remember, I showed the WDM longer link. Okay, after the transmitter, you have a booster amplifier. Okay, so you can so to boost the level of the transmit signal in a longer link, you can put a booster amplifier. Okay, so that's the thing. Also, sometimes if you look at networking as optical networks, you take an optical node. Okay, you can have an amplifier within the node. Why? To overcome the losses to the switches and cross connects and so on. That's possible. But in a longer link, you have a transmitter, then you have a booster amplifier.
Yes, correct. Yes, sir. And next question is, sir, which simulation tool can be used to simulate the hybrid WDM, TDM passive optical network? Shall I read again?
Yeah.
Which simulation tool that can be used to simulate the hybrid wavelength division multiplexing, time division multiplexing, passive optical network?
Again, you can look at some commercial design tools like VPA transmission maker, and most of them, yeah, you are talking about all the different TDM, WDM, all the combinations, I guess. So I would ask you that madam to look at VPA transmission maker or OpSim modules. Maybe they model all those things. I know for sure WDM is modeled there, but optical TDM, I'm not sure. So one can check that.
Oh.
Okay. Yeah.
Okay, sir. So the last question is there any relationship between bitrate and the bandwidth of optical bandpass filter in inline EDFA system?
Okay, inline EDFA system bandwidth of the say bandwidth optical filter.
Yes, sir.
No, normally, okay, here it is. Optical filters are used at the receiver point. Okay. Bandpass filter, optical bandpass filter is used in the receiver point or at the destination point. Inline EDFA has its own bandwidth, right? Okay, it has its own bandwidth. So let me understand the question. So assuming it is a filter in the optical amplifier. Repeat the question.
Is there any relationship between bitrate and the bandwidth of optical bandpass filter and optical bandpass filter inline EDFA system?
Okay. I understand. So you're talking the relation between any impact on the bit error rate and the optical filter bandwidth.
Yes, sir.
Well, certainly there is a definitely impact between the bit error rate and the optical filter bandwidth. If you have optical filter in the inline system or before the receiver, yes, you need to provide optimum optical filter bandwidth. If you have let's say you need optical filters in the WDM links to minimize the AC noise, right? Amplify spontaneous emission noise. So to remove this AC noise, what is the optimum filter bandwidth? One has to look into that. That's the optimization problem. Yeah, sure, definitely. For if you have a very, let's say if you have non-optimum filter bandwidth in the link, then bit error rate, will be high. Okay, if you have optimum filter bandwidth, suddenly bit error will be low. So yes, there is always an optimum filter bandwidth that impacts the bit error rate. That's true. A lot of simulations and the analysis has been done with respect to this problem. Okay. Yeah.
Yes, sir. Right.
So
Thank
filter
you.
filter bandwidth has to be optimized for the proper BER. Okay.
Okay, better, right. Yes, sir.
Okay.
Thank you. Thank you very much, sir. Really, we are very lucky to have you speak about this interesting topic. On behalf of Vidyavardhaka College of Engineering, ECE department, and entire staff, I wholeheartedly thank you very much, sir, for providing these wonderful insights about the software modules and their performance along with the some demo. I'm sure that the participants.
No, I was not able to do any demos today because it was a virtual presentation. Maybe after the virus is over, next year when I come to Mysuru, suddenly I will give a visit and do the demos at your campus. That will be better.
Definitely, sir.
Okay.
Participants must have benefited immensely by attending your session, sir. Very grateful to you, sir. Thank you very much.
I wish I would have been there, in person, but doesn't permit at this point. Maybe in the future, near future, we can do this. Okay.
Yes, sir. Thank you.
Okay.
Thank you.
Thank you very much. Okay. Then I will close my system. Okay. Yeah.
Yes, sir. Yes, sir.
Very good.
Thank you, sir.
Okay. Thank you very much.
Thank you.